This is the third and final video in my series discussing section 4.1 on maximum and minimum values. In this case, we're going to be talking about locating absolute maxima and minima. So remember that the general idea of what we're talking about in this section is that we're looking for high points and low points on a graph. The highest point on a graph is what we call the absolute maximum, and the lowest point on a graph is what we call the absolute minimum. Now we've seen some functions that don't have either an absolute maximum or an absolute minimum, but it turns out that if your function is continuous, so it doesn't have any jumps or breaks or asymptotes or anything like that, and it's defined on a closed interval from a to b. So remember that this notation means all the numbers from a to b, so from a to b, including a and b. So those square brackets there mean that a and b are included. Another way to visualize this is that our function starts at a point A, ends at a point B, and is defined all the way from A to B. So on that interval that includes A and includes B, if your function is continuous, you always have an absolute maximum and an absolute minimum. But the question is, how do we actually find these points? So let's look at an example. The absolute maximum, minimum on a closed interval can occur in one of two ways. There's sort of two ways that this can happen, two scenarios. One is that the absolute maximum or minimum occurs at a local maximum or minimum that happens at an interior point. In this case, that's how we get our local minimum for this function. This function has an absolute minimum at this value C2, and that absolute minimum happens to also be a local minimum, happens to also be a critical point where my slope is 0. You can see here if I were to draw a tangent line, I would have a slope of 0 there. So that's a local minimum that happens to also be an absolute minimum. The other scenario is that the absolute max or min occurs at an endpoint, and that's what's happening for this function. For our absolute maximum, the highest y value for this function is occurring at this point x equals b, which is an endpoint. Now that absolute maximum is not a local maximum. Remember that we talked about how local maximums don't occur at endpoints. All right, what else is going on with this function? So at this point C1, what we have is a local maximum, but it's not the absolute maximum. It is a high point, but it is not the highest point of my function. So that's a place where I have a local maximum, where I have a critical point, but I don't have an absolute maximum. And then finally, this point A, that's an endpoint. It's not a local minimum because endpoints can't be local minimums, but it's also not an absolute minimum because it's not the lowest point on my graph. So this is not a local min. It's also not an absolute min. So take a look at that, right? So we've got some critical points. The critical point at C2 is the absolute minimum. It happens to also be a local minimum. The endpoint at B is where our absolute maximum is, but endpoints cannot be local maximums. We've got a critical point at C1 where we have a local maximum, but that's not an absolute maximum. And then we've got our other endpoint at A, which is not a local minimum, but it's also not an absolute minimum. Okay, so here's how we're going to do this. So we're going to be given a function that's continuous and defined on a closed interval from A to B. So you're going to have, those are going to be specific numbers in the problems that you'll see in just a minute. So the first step is going to be to find all of those critical points that lie in the interior. Remember that endpoints can't be critical points, so we want to find all of the critical points that are actually in that interior between A and B. So then what we want to do is plug all of the values that we have, the two endpoints A and B, and all of the critical points that we found in step 1. We plug them all into the original function f. And the highest function value that we find on that list is going to be our absolute max. The lowest function value that we find on that list is the absolute min. So that's the outline. Feel free to kind of pause the video, write this down, right? This is good stuff to know. And I'm going to work through some examples here in just a second. Okay, so here's an example. So I've given you a function. That's a continuous function. It's a polynomial. And way back when we talked about how all polynomials are continuous. and we want to find the absolute maximum and minimum values of f of x on the interval from -7 to 7. So our first step is to find the critical points. What are critical points? Critical points are places where my derivative is either equal to 0 or undefined. So I'm going to take the derivative. So I take the derivative, I get f prime of x. This x cubed over 3, I could use the quotient there, but I'm going to be a little bit clever and write that as 1/3 x cubed, so that when I take my derivative, I get 1/3 times 3x squared. And then minus 9x, the derivative is minus 9. So that's going to work out to be x squared minus 9. That's never undefined because it's a polynomial. I set it equal to 0 to find my critical points. I add 9 to both sides, take the square root of both sides, I get plus or minus 3. Remember, when you take the square root of both sides, you always get a plus or a minus. Now, my interval is -7 to 7. Are the numbers that I found between -7 and 7? Yes, they are. So these are both in the interval from -7 to 7. So those are both critical points that I want to care about. If I had found any other critical points that were either bigger than 7 or less than -7, I would have thrown those critical points away. So now I'm going to make our list. So we're going to have our function values at critical points and our endpoints. The critical points we had were -3 and +3, and the endpoints are -7 and +7. So we're just going to plug all of those into the original function. Make sure that you're plugging into the original function here. Don't plug into f prime, plug into f. So this is going to be -3 cubed divided by 3 minus 9 times -3, +3 cubed divided by 3 minus 9 times 3, -7 cubed divided by 3 minus 9 times -7, 7 cubed divided by 3 minus 9 times 7. And I'm just going to use my calculator and plug all of that stuff in. So using my calculator, I get 18 here. I get -18. I get about -51.33, and then I get 51.33 here. So the highest number on that list, which is 51.33, that's my absolute max. Absolute maximum. And then the lowest number on my list, that's going to be the -51.33. That's going to be my absolute minimum. So that's how we do it. So again, process here, we find our critical points by taking the derivative, figuring out where that derivative is undefined and where it's equal to 0. We take our list of endpoints together with any critical points that we found, and we plug them all into the original function and look for the biggest and the lowest y values that we get back out. All right, we're going to work through this example pretty much the same way. We're starting with our function g of x. We're going to find the derivative. We're finding the derivative so that we can find the critical points. Remember, the critical points are the places where the derivative is equal to 0 or where the derivative is undefined. So when we take our derivative here, we're going to need the product rule. We've got x times e to the minus 2x. So the derivative of the first function, that's 1. The second function, that's e to the minus 2x. The second function is x, and the derivative of e to the minus 2x is e to the minus 2x times -2. That times -2 there is coming from the chain rule. Now that's never undefined. There's no values of x that I would not be allowed to plug into any of those functions, so the only thing I have to worry about is setting this equal to 0. Now, this looks pretty complicated, but when I try to set this equal to 0, what I notice is that I've got an e to the minus 2x in this term, and I've got an e to the minus 2x in this term. So I'm going to factor that out. I factor out the e to the minus 2x. I'm left with 1 minus 2x. And the reason why factoring is helpful there is now what I know is that one of these two factors has to equal 0. The only way you can multiply two numbers together and get 0 is if one of the two numbers was 0. So either e to the minus 2x equals 0 or 1 minus 2x equals 0. Well, if 1 minus 2x equals 0, add 2x to both sides, I get x equals 1/2. And e to the minus 2x equals 0, if I think about this equation, what I will hopefully realize is that, you can't raise e to a power and get 0. There's no way to raise e to any power and ever get 0. So this has no solutions. So we only get one critical point, which is x equals 1/2. But what we have to ask ourselves is this in the interval that they gave us? Is this in the interval from 0 to 2? Because if it's not, then we're going to take that critical point and throw it away. We're not interested in any critical points that don't live in this interval. Because the interval is 0 to 2, and because 1/2 is between 0 and 2, we don't throw it away, we keep it. So now we're going to make our list of function values. So what goes on the list? We're going to plug both of the endpoints into our function. And again, we're plugging into the original function here. And then any of the critical values that we found and didn't throw away, we're going to plug those in too. So we've got one critical value and 2 endpoints, so we're going to plug in 3 values to our original function. So f of 0, that gives us 0 times e to the negative 2 times 0. F of 2, that's going to be 2 times e to the negative 2 times 2. And then f of 1/2, that's going to be 1/2 times e to the negative 2 times 1/2. Plug all those in. I'm using my calculator here, and I worked out that this first one is 0. The second one is 0.0366. And the last one is 0.1839. All right, and if I'm looking at those numbers, I'm looking for the biggest number on that list. And the biggest number on that list is 0.1839. So that's the largest value, so that's my absolute maximum. And then 0, that's the lowest number on this list, so that 0 is my absolute minimum value. Okay, so that's the basic process here. So we're going to take our derivative, set it equal to 0, look for critical points that are actually in the interval. Any critical points that we get that are not in the interval, we toss in the garbage. And then everything that's left, plus the 2 endpoints, we plug all of those into our original function, and then we're just looking for the biggest number on the list and the lowest number on the list. So that's it for this section. We've got these 3 videos, we've got lots of practice problems, work through those. Let me know if you have any questions, and I'll see you in the next section.